This is a video of the graphing polynomials unit test review, and this is going to be questions 4, 5, 6, and 7. Starting here on problem number 4 without graphing in our calculator, we're going to state the degree, the number of roots, the multiplicities of each root, the behavior of the graph at each x-intercept, whether it crosses or touches, and what the graph looks like at each x-intercept, whether it's linear, whether it's quadratic, whether it's cubic. You might find it helpful to draw yourself a rough sketch of the function based on its roots to help you determine the end behavior, sometimes abbreviated as EB. So first of all, even before we look at maybe a rough sketch, we can identify a couple things about this problem, and one of them is the degree of this problem. And just a reminder that what we do is we go back and we look at the multiplicity on here of a couple of these values. And when I'm looking at the multiplicity, I'm looking at that 3 right there, the exponent on that parentheses, and also the 2 on that exponent. And if we add those two yellow dots together, 3 is one of the exponents, 2 is one of the exponents, and we're going to get a value then for our degree of 5. And what do we call a 5th degree polynomial? Well, it's called a quintic. Q-U-I-N-T-I-C. Some of you are asking, why didn't we do 0.5 to the first power? Well, there's no variable with 0.5. So we don't have to look at an exponent on a constant value. We're looking at it when it applies to a variable. So consequently, degree is 5. We call it a quintic. That means if our degree is 5, then the number of roots are going to be 5. We can see from our equation there that our leading coefficient is positive, 0.5, positive. Maximum number of turning points. The turning points are 1 less than the degree, so we're going to have 4. And here's where we might want to look at the rough sketch for a minute. And before I do, we might want to take a minute here and get one more piece of information. And that's, I'm jumping down here to the box, and what I'm going to put in this box is going to come from the fact that we have x minus 7 equals 0. One of our parentheses up there, we add 7 to both sides, and we get x equals 7. Our multiplicity on this variable, or yes, for this root, is 3, the exponent on the parentheses. Because 3 is an odd number, we're going to cross, and then we ask ourselves, well, is it linear, is it quadratic, is it cubic? Well, it's cubic. That's going to help us draw the picture here momentarily. We also have another parenthesis that has an x plus 2 in it. So let's subtract 2 from both sides to get our root, which is where this graph is going to cross or touch the x-axis. The multiplicity on this one is a 2. Because the multiplicity in this particular problem is even, we are going to touch the x-axis. And then we ask ourselves, well, is that linear, is it quadratic, is it cubic? Quadratic. So now, when we come back and look at the picture, and this is going to be a very, very rough sketch, but we know that 7 is somewhere off here to the right, and then negative 2 is off here to the left. And when we draw this, because 7 has a multiplicity of 3, and it's cubic, we draw it as something kind of squiggly. Over here, our multiplicity for the x equals negative 2 is an even number. We're going to be touching that, and I believe that it's gonna, let me try that one more time. Gonna look something like this. And somewhere way down here, our graph would probably connect. And now what we can see is we can see our end behavior as x approaches negative infinity. Our graph is going downward towards negative infinity. As x approaches positive infinity, we didn't even really need to have the picture to draw this because we know our leading coefficient is positive, so we're going to finish going positive, which is going upward towards positive infinity. Finally, the domain of our function, our domain is all reals. But our range is not all reals, and oftentimes what we ask ourselves when we're dealing with this is we say, do we have a high point? Do we have a low point in the graph? And actually I'm mistaken on that, because as I ask myself that question and I look at my picture, I think, no, I don't have a high point or a low point on the graph. To the left, my graph keeps going downward, and to the right, my graph keeps going upward. And because our end behavior is going in opposite directions, we do not have a high point or low point, so our range is actually all real numbers as well. By the way, I know it says without graphing it in your calculator. Worst comes to worst, draw it in your calculator. It's not going to show up very well, at least not the whole thing, but at least it might give you some idea of the rough sketch for you to be able to identify the end behavior if that's what you're struggling with. We've got some of these same concepts in this next question here, and I think I must have been thinking about this next question as I was finishing up that last one. But this time we've got f of x equals negative 0.25x squared times the quantity of x minus 5 times the quantity of x plus 6. Well, once again, we need to look at our multiplicity, so to speak, to be able to identify the degree. And there's no exponent on that parentheses with an x minus 5 in it, so we can put a 1 in there. And there's no exponent on the x plus 6, but we can also put a 1 in there, and that can help us determine the degree of our function, which is 2 plus 1 plus 1, which is 4. And if you've been working through your paper at all, we've actually classified a fourth degree polynomial once before. This is a quartic. Because our degree is 4, we will have the same amount of roots, so that is also 4. As we look at our leading coefficient, the number in front of the 0.25x squared is negative, so we're going to have a negative leading coefficient. The maximum number of turning points is 1 less than the degree of our function, so it's going to be 3. And our end behavior, because our leading coefficient is negative, we're going to finish our graph negative. To the far right, when you look at the picture, we should be going downward. But this degree is even to the fourth degree. It's an even number, so our end behaviors are both going to be going in the same direction. Evens go in the same direction and odds go in different directions. And over here, when we want to come up with our values, it is our first value is going to be 0. Now, some of you might look at this a little bit differently, but x is 0 and it has a multiplicity of 2. So what I did is I really took negative 0.25x and I set it equal to 0. If we divide both sides by negative 0.25, we still get 0. So x equals 0. The exponent is the multiplicity here, and because 2 is an even number, that means that we touch the x-axis. And then if something is to the second power, is it linear, is it quadratic, is it cubic? Well, it's quadratic. So we go to the next parentheses, and I'm squeezing it in here, but it's x minus 5 equals 0. If you even need to write this down, but we end up with x equals 5. We just wrote in the exponent a moment ago when we were looking at the degree of this entire function, and we say that the exponent on there is 1, because 1 is an odd number, that means that we're going to cross the x-axis. And because with the 1 there, x to the first power, is it linear, is it quadratic, is it cubic? Well, it's linear. So once again, we go through the same process when we get over here to our last parentheses of the x plus 6. We subtract 6 from both sides to get x equals -6. The multiplicity is determined by the exponent on the parentheses, which is a 1. So this is also going to cross because 1 is an odd number. And just like the box before here, it's linear. To find the y-intercept of the function, what we need to do is we need to let x equal 0. So as we determine this algebraically, we're going to put 0 back into our function here, wherever we see x, and we end up with negative 0.25 times 0 squared. And then we have 0 minus 5. And then we have 0 plus 6. When we multiply these all together, this is negative 0.25 times 0 times negative 5 times 6. We've got that 0 in there. This is equals 0 when we multiply those all together, so our y-intercept is equal to 0. And we can show that here in a moment as we are going to graph this. I actually have the equation already typed into our function. But what I don't have typed in is I don't have typed in the window, because you've got that box off to the right of your paper there above the grid, and it says for our window that we're going to leave the x's alone. X minimum is -10, x maximum is 10, and our scale is 1. We're still going to leave our y minimum as -10, but our maximum now is going to become 80, and our scale is 10. And now that we've got the equation typed into our function and we've got our window in here, let's draw the picture. And I'm going to scan that into here. So here's what our picture looks like. And what we were just talking about here a moment ago is we said that the y-intercept is 0, 0. Notice that here on our picture, we've got 0, 0 right here. And that actually ends up to be one of our turning points, so we might need that information in a couple minutes. But the other values that we need to figure out are here. And that's where I'll start, actually, before I put another dot on that. I'm going to start with that. So we go back to our picture, and we're going to press second and trace, and it's a maximum value. And we're going to scroll. Somewhere about here, and enter. A little bit to the left. Now we're going to go a little bit to the right, and enter, and then enter one more time. And we get our value there of negative 4.26. It says round to the nearest 10. So we got negative 4.3 and then 73.1. So we'll fill that in. Negative 4.3 and 73.1. We're going to do that again to find this point over here. also known, this one here to the right is a relative maximum. Coming back to our screen here, and we're going to have to scroll. We're going to have to do second, trace, and maximum. And then we're going to scroll through here. And it's going to take me a couple minutes, and I hope that the screen doesn't go wacky. But we'll do the best we can. A little bit to the left, enter. A little bit to the right, and enter one more time. And down here at the bottom of our screen, we see that we've got a maximum at 3.51, which rounds to 3.5, and then 43.64, which rounds to 43.6. 3.5 and 43.6. So we've used the graphing calculator to graph the function, we sketched it, we've labeled our relative maximum and minimums on our sketch, we rounded to the nearest tenth, but now what we want to do is we want to identify the intervals over which the function is increasing. So start left on your graph, and what happens is when we start left, we're going upward until we get up to our maximum value here. So this is going to be we're increasing from negative infinity to negative 4.3. We use x values to identify this, and I'm gonna go back to my highlighter for a second so you can see we started at negative infinity and we went up to here. But when we get up to there, what's going to happen is we're going to start changing direction. That's why it's called a turning point, and we're going to start going downward. And unfortunately, my highlighter is turning it into lines, but at least I hope you can follow along, because now what we've got is we went from negative 4.3 at x value down to the x value of 0. But once we get down there, we change direction again, and I wanted that to be a yellow color, so I'm going to continue with yellow. And now it's yellow. And when we go in that direction, we're going upward, which is an increasing function, or increasing part of the function. So we're going to join that, and we're going to say, well, we went from 0 to the x value, which is 3.5. And finally here, when we go back to our highlighter, we start going downward. But when we go downward, that is going to be, one more time, that is going to be from 3.5 to positive infinity. We're looking at the x values. I know we're going downward. Our end behavior is going down to negative infinity, but we're going right on the graph. So we're going to positive infinity. When we look at our domain, well, the domain of most graphs in Algebra 2 is all grids. Not all of them, but most of them. Our range on this one, however, is not, because what we need to ask ourselves is, do we have a high point or do we have a low point on the graph? And we have a high point, and we really do this time. It's this negative 4.3, 73.1. That is the highest point in the graph. So we can say that our range is negative infinity to 73.1. We're going to put a bracket around there because 73.1 is on that graph. And then we have a parentheses. All of the points are below 73.1. So it's negative infinity, we start bottom, and we go up. So we've talked a lot about degree and turning points. multiplicity. So let's sketch a polynomial with the following characteristics. If possible, try to create more than one. So the first one is a third degree polynomial, and remember, when we see third degree, the first thing that we think is two turning points. Negative leading coefficient means that we're going to finish going downward, so to the far right, and then we're going to have two real roots. So we need two roots on here. Third degree means that the end behavior is going to go in opposite directions. So I'm going to have over there to the left, we're going to be going upward, and over here to the right, we're going to be going upward towards positive infinity and downward towards negative infinity. So we can draw something like this. And I kind of missed it there, but there's one root, there's two roots. We're going up one and down, up to positive infinity on the left of this graph and down to negative infinity on the right. So we do have negative leading coefficient, and we've got 1, 2 turning points. Another way to draw that is we could just change this around a little bit to something like this. We still have 1, 2 turning points, so we have a third degree function. As we look to the right, we did finish going down towards negative infinity, and we've got 1 root and 2 roots on our graph. If we look at number 7 here, our fourth degree, and we're looking to draw a fourth degree polynomial, a positive leading coefficient, and 0 real roots. Well, in this particular case, fourth degree has 3 turning points, 1 less turning point than the degree. Positive leading coefficient, so we're going to finish going upward. And in fact, because it's an even degree function, they're both going to be going upward. And we're not going to touch the x-axis because we don't have any real roots. So 1, 2, 3 turning points. So let's check. 1 turning point, 2 turning points, 3 turning points. We finished to the right going up towards positive infinity, and we never touched the x-axis. And it turns out that we cannot draw another picture like that.